Well, my mechanical friend, would you like to learn a little bit about surface area? Okay, then that's what we're going to talk about today. We're going to look at the surface area, which in a picture would be describing something like, this is an example, if we have a function like this paraboloid, upside down paraboloid with circular cross sections. Notice that what's under the x squared and y squared are equal, so circular cross sections. Maybe we would even say the contour map would just be circles, so you should understand that all right. But this is above the region R, where x goes from -2 to 2, and so does y. So I have the square region in the xy plane with this paraboloid above it, and the question is, how would we compute the surface area of the paraboloid above this particular square? Now, this is just a generalized example to show you how to do it, and we may eventually come back and do this very example, but just to try to describe how to do this, actually by summing up a whole bunch of areas of pieces of this thing. So, of course, you probably know, first thing we want to do is divide this region R up into rectangles, and it will cut off above a small rectangle would be the shape of this would be a parallelogram, possibly a rectangle for this one since it's so symmetric, but normally some kind of parallelogram. And if we added up the areas of all the parallelograms above all the little rectangles that are in our region R, and then of course we're going to let the size of the rectangle approach 0, you could see that that Riemannian sum would give us the area, give us a good approximation until we say the maximum of the rectangle goes to 0. Once we say that, it'll give us the area. So now the question is, how do you find the area of one of these parallelograms? And here's the interesting part. If we looked at each parallelogram, it spanned, I don't want to say spanned, but you know, when we find the area of parallelogram, it's you could think of it as the cross product, or the length of the cross product of two particular vectors. And one vector would be the one describing the slope in the x direction, and the other would be that is in a constant plane for y, and the other one would be in the y direction, the slope in the y direction. So if we take the vectors representing the slope of a piece this way and the slope of a piece that way, which is what I'm saying right here, understand for a delta x, then this would be the slope, and this would be times delta x, whatever delta x is, times k, and this will give us a vector describing, actually that one would be this side of this parallelogram, and this one should be describing this side of this parallelogram. And in order to find the area of that parallelogram, remember that that's the length of the cross product of these two vectors. The area would be the length, or maybe I should say the length of the cross product of these two vectors is the area of the parallelogram that they span. Okay, well, since that's true, then we'll go ahead and find that cross product. Remember, the mnemonic way to remember that is a determinant with I, j, k in the top row, and then the components of the vector. The I component here, the j component is 0 for this one, and the k component out here. And then we could find that cross product. Now, it's a little torturous to do that, but not terribly bad. This would be I times 0 minus delta y times fx at xi yi delta x, as you see here, and then minus j times its minor, which would be delta x times delta xi times delta yi times the partial derivative with respect to y, at xi, yi, and that's negative because of the position of the j. And then finally, plus k times delta x times delta y. So there that is. That is the cross product of vectors. And if you want to find the length, of course, you find the square root of each of the components squared. So that's pretty easy to do. But notice what happens since you have a delta xi, delta yi in each of the terms underneath there, then and it's squared in each of the terms underneath there, then we could factor it out, take the square root, and it comes outside the radical. Here it comes, right? And then so what we would have left would be this part squared plus this part squared plus 1 squared, which is still 1. I guess I could have written 1 squared there. That somehow would fit a little better with this. But and of course, when you square a negative, you get a positive, and so there's no reason to leave these as negatives here, here, and no reason to say 1 squared anymore. But notice that this delta xi, delta yi is really the area of the rectangle down here. Right. And so the sum of all those parallelograms would be approximately the area of our surface, right? And if we say let the maximum of the delta AI approach 0, then we can approximate this with the integral of the following. Okay, and here's the answer. If f is its first partial, if f and its first partial derivatives are continuous on the closed region R in the xy plane, then the area of the surface S given by z equals f of xy over the region R is given by the formula surface area equals double integral over region R, and you can get the limits from looking at the region, and see the dA. Well, that's going to depend on which one, how you set up your limits, whether that's dy dx or dx dy. Actually, we might wind up substituting r dr d theta for that anyway. So 1 plus, and that's, here's the 1, plus this squared plus this squared. So notice how close that is to the arc length formula. When we're in 1 dimensions, of course, arc length has a 2-dimensional correspondence with surface area, as you might expect.